Last time we started talking about chapter 14. Again, we're talking about sort of phase changes here, energy associated with phase changes. We also saw and talked a little bit about, I think, towards the end there, that there's a certain amount of energy required, really, just to change the phase of a substance. For example, taking it from solid to liquid, or backwards liquid to solid, or liquid to gas, and so forth. And as we talked a little bit about before, that's what's referred to as a heat of fusion for going from solid to liquid. And in terms of going from liquid to gas, that is the heat of vaporization. We'll see that a little bit more today. Yeah, again, a reminder today, as I put out in the announcement, we are doing the precipitation experiment. I forget that's, I want to say it's number 18, I think it is. So that's what's on tap for today in terms of lab. We also talked about that the energy associated with keeping something sort of in its same phase, as we'll see today as well, again, is what we saw earlier on in an earlier chapter, which was that specific heat. So again, if we sort of change something in terms of their temperature, but the phase remains the same, and we're interested in terms of the energy associated with that, that is basically our specific heat equation, as we talked about. If we're interested in keeping something the same temperature and changing the phase, then that's the heat of fusion, heat of vaporization. Remember that when we do change phases, it does occur at the same temperature. So, for example, like water at 0 degrees Celsius, that's when water goes from solid to liquid, and vice versa backwards as well, liquid to solid. Again, it occurs at the exact same temperature. Really, the only difference is in terms of the energy. Are you putting more heat and energy in, which would be endothermic? Or are you kind of removing or giving off heat and energy, which would be exothermic in that sort of process? Okay, so I think that's about where we're at here. So let us talk about that there. All right, get some stuff out of my way here. All right. So remember though that when we do a physical change and we take a substance, say from solid to liquid, or vice versa, or whichever sort of phase changes you want to occur, remember that we're really not changing what the substance is. Remember, that's a physical type change. So, for example, in the case of water, if we started with ice and then we ended up at liquid water, fundamentally it is still H2O. It's just in a different sort of phase. So, really, what comes into play, as we will see, is was referred to as intermolecular forces. And I think we might talk a little bit about this as well. These are the forces that basically hold one molecule together with another molecule. We will not be talking about Gibbs free energy, I don't believe, in this class now. If you take 1B, you'll talk about Gibbs free energy. So when we do that, what has to happen, when we heat something, say like water at its boiling point, what we're really doing at that point is there's a certain force that holds, again, one water molecule together with another. As we'll see again, water is polar, so oxygen is more negative, hydrogen is more positive. So you have this sort of attraction between the opposite charges. And it is this force right here, which is our intermolecular force, that really gets broken as we basically heat this. So as we heat this, it is this force right here that holds this entire water molecule together with this entire water molecule. And when we break that, for example, as going from liquid to gas, they're able to obviously go off into the gas phase and separate from each other. And again, as we talked about, there's a certain amount of energy associated with doing that. So when a substance goes from solid to liquid, again, we're not fundamentally changing it. We're not breaking the internal bonds, which are sometimes referred to as the intramolecular forces. And those are, again, the forces within a single molecule. So when we talk about one single water molecule, we're talking about the oxygen hydrogen bond on one side, the oxygen hydrogen bond on the other side, essentially the covalent bonding, the sharing of electrons, and even ionic bonding is also intramolecular forces. And those are really, really strong forces. And I think, as we might have touched upon last time as well, that's why when we do go, say, and boil water, we don't get like hydrogen gas and oxygen gas that develops, but we do get water vapor or steam that basically occurs. And again, it's because we're not breaking those really strong intramolecular forces. We're breaking the weaker intermolecular forces, the forces that are between different molecules. So as energy is added and the molecules again start to increase motion, it eventually creates greater movement. It allows them more energy basically to break apart from each other, and they're able to basically go from one phase to the next. Remember, in the solid phase, most substances are pretty much packed in there very tight to each other. They don't really have enough energy really to pass one another in terms of their molecules or atoms or anything like that. When we get into the liquid phase, they gain enough energy where they actually can sort of pass each other and move a little bit more. And again, that's why when we think about a liquid, it's more fluid, right? Obviously, than a solid. And obviously, when we get to the liquid to gas transition, we need to put energy in there. As they gain enough energy, they are able to again break apart from each other 100%, start flying around in the gas phase, causing those collisions, the pressure that we talked about with gases. These are all sort of endothermic processes. Remember that when we add heat or energy is absorbed, that's an endothermic process. And again, in terms of energy or values, those are usually positive numbers when you calculate them. And again, a reminder, pretty much going the opposite way. So if we were going kind of this way or this way, again, those would be more exothermic processes in terms of the heat and energy, which means heat and energy is released. And in terms of numbers, as we've seen when we talked about specific heat, those are typically our negative numbers that we associate with those processes. Any questions on that so far? So, as I talked about a minute ago, and I think we touched upon it last time as well, there really are these two sort of main forces that we come across sort of when molecules sort of behave. And the first one, again, as I mentioned before, is the intramolecular force, as the name implies. And as we talked about, that is within a single molecule. And again, those are always stronger than intermolecular forces. Again, the reason for that is we know when we heat something, we typically don't get like alphabet soup, like all the elements just basically fall apart from each other. So what ends up happening is one molecule and another molecule basically separate from each other. And we know that the intermolecular forces are much weaker. Now, intermolecular forces, as I said, is those forces that really do hold one molecule together with another. And they are a lot of times responsible for things like melting points, boiling points, and so forth. When we have a very strong intermolecular force, we typically see higher boiling points and melting points. And that's because the strength between one molecule and another is very strong, which means it typically will take a lot more energy to break those guys apart. And a lot more energy usually translates into a higher boiling point and so forth. So we do look at intermolecular forces, what type of intermolecular forces are there, as to what we can predict in terms of things, like I said, in terms of sort of boiling points and melting points and those type of things. So here again, an example of what I drew earlier. That force that holds this one water molecule together with another is our intermolecular forces. The individual bonds within the molecule are the intramolecular forces. And again, that's why we don't get that alphabet soup when we heat something like water. We touched upon this, I think, when we were looking at sort of the heating and cooling curve. But when we do those transitions, as I mentioned before, there is a certain amount of energy required, again, to do nothing more than simply take a substance from solid to liquid, or vice versa, backwards, or take something from a liquid to a gas. And that is what we touched upon earlier. That is the heat of fusion, is sometimes referred to. So this is sometimes referred to as the heat of fusion. And it is really just the energy to take solid to liquid or liquid to solid. Remember, this occurs at the same temperature. And for example, for something like water, it is 0 degrees Celsius where that occurs. And this is the heat of fusion for water. It's about 6.02 kilojoules per mole. I think I wrote out the other day sort of the translation of that to joules per gram, which is also another common sort of number that is used. And excuse me, that would be something like 334, 35, 33, depending on your rounding, 334, we'll call it, joules per gram, give or take. And that basically means you need to put in there 334 joules for every gram of water to get it to change from the state of solid into liquid. And again, depending on which way you go, the number will be the same, but the sign will be different. So again, if we were doing the solid to liquid transition, it would be positive 6.02 kilojoules per mole. And if we're doing the opposite transition, liquid back to solid, it would be negative 6.02 kilojoules per mole. Again, the number would be exactly the same. The sign will be different because we're doing a different transition. Same thing here. This guy would be positive and it would be negative, like 334 joules per gram, going the opposite direction. The heat of vaporization, which is what this is referred to, delta H of vaporization, um, is the energy required to do that other transition of going from liquid to gas or gas back to liquid. And again, for water, this occurs at 100 degrees Celsius and is 40.6 kilojoules per mole, which give or take is about 2260 joules per gram. And again, it's positive or negative, depending on which way you kind of go. Like if we're going from our liquid to gas, that's endothermic. We need to put heat and energy in there. That's going to be our positive 40.6 kilojoules per mole. If we're going from gas back to liquid, we need to give off that energy. That's going to be minus 40.6 kilojoules per mole. So again, these numbers are going to be the same regardless sort of which way you're going. Just like we talked about with specific heat, we want to make sure that we use the correct sign, depending on whether it's endothermic or exothermic. Also a reminder that the numbers that we're seeing here, the 6.02, the 334, 333, the 40.6, and the 2260, those are all specific for water. So if you're not dealing with water, other substances will have different values for heat of fusion and heat of vaporization. And in addition, remember that we commonly think about sort of freezing point as 0 degrees Celsius, boiling point is 100 degrees Celsius. But also a good reminder is that is also specific for water. So if you're not dealing with water, you might have different boiling points, different melting points, freezing points, and you would have different values of delta H of fusion and delta H of vaporization as well. So again, although these are the most common ones we come across a lot, there are other values for other substances, and really this stuff is specific for water here. Any questions on that there? So this again is sort of a heating cooling curve that we saw earlier as well. And when we do calculations, and I think we touched upon it as well, the thing to keep in mind is there are certain parts of this curve that you want to make sure that you understand. So again, at 0 degrees Celsius here, this transition exactly at 0 degrees Celsius is when we go from solid to liquid or liquid to gas. And again, that would be where we would use our delta H of fusion. Same thing at 100 degrees here, since this is for water. At 100 degrees Celsius, we would do our transition from liquid to gas and gas back to liquid. That's our delta H of vaporization. Again, pretty much down here, this kind of curve that goes upward is something that's in the same phase, but different temperature. So this part of it here, we would use something like our specific heat capacity equation, Q equals ms delta T. Again, anywhere where it kind of goes upward implies that the phase is the same, but the temperature is changing. So again, wherever we kind of have that situation, if we wanted to calculate the energy, we would use our specific heat equation that we saw earlier on in chapter 10, maybe, I think it was. And here as well, we have that same guy all the way through in the gas phase, also using Q equals ms delta T. So sometimes it's very helpful to sort of draw this little curve here. And really, you could kind of visually walk yourself through these transitions. We're going to do an example here in just a sec, kind of doing the calculations, but sometimes it's helpful. But essentially, anywhere on the curve where you kind of have a flat line, plateaued line, that is a phase change, and that is where you should either use delta H of fusion or delta H of vaporization. Anywhere where you got the curve kind of going upwards like that, that is a specific heat sort of situation in terms of using it. Also, I think we touched upon it last time as well, but again, a good reminder that S, which is our specific heat capacity, and that is, if you remember, for liquid water, the number that we've used a lot, which is that 4.184 joules per gram per degree Celsius, or that 1 calorie per gram per degree Celsius, again, for liquid water. And it's really important to remember that specific heat capacity will change with the state. So you would definitely want to use that 4.184 number in this state of it if you're dealing with water. You would not want to use it up here. You want to make sure you get the S for water in the gas state. Just like down here, you would want to make sure you get the S, for example, for water in the solid state. And they are different values. So again, they're about 2 uh, joules per gram per degree Celsius rather than 4. So when you look up that value, for example, on the table, again, you want to make sure you get both the substance and also the correct state. Otherwise, you will end up with perhaps the wrong value there. Any questions on that? All right. So which you predict would be larger in a substance, the delta H of vaporization or the delta H of fusion? And I think we also touched upon that, and you could actually see it on the little curve we just looked at. So this was kind of the curve, if you will. And this was the transition from solid to liquid. This was basically the transition from liquid to gas. And as we talked about, I think last time, it does take a lot more energy to do that transition of going from liquid to gas versus solid to liquid. And that's because in solid to liquid, everybody is pretty close to each other in the solid phase, and in the liquid phase, they're still relatively close to each other. There's a little bit more room for movement. But when we go from the liquid phase where there's little room for movement, they're close to each other, to the gas phase where they've completely broken apart and starting to fly around from one another. So it always takes a lot more energy to do this transition than it does the solid to liquid, or going backwards as well. And we see that with the numbers. So if you remember, I did a little calculation just a second ago for water. This is something like 334 joules per gram. For water, this is something like 2260 joules per gram. So if you just compare those two numbers, it's about 7 times the amount of energy required to do the transition from liquid to gas than it does from solid to liquid. Again, because at that point, you're completely breaking everybody apart. So in this case, it would be the heat of vaporization should usually be the larger value for a substance. Because of that, again, takes a lot of energy to completely get everybody away from each other into the gas phase. Any questions on that? So the unusually high value for the more heat of vaporization for water is an important factor. Again, why we talk about, for example, something like uh, the temperature of water is rising and stuff like that, because it does take a lot of heat and energy to make even a little bit of water change its temperature by 1 degree Celsius, and that implies obviously things are warming up. So, for example, if we had 10.5 grams of liquid water and we want to calculate the amount of heat required for it to evaporate, what we are doing here is going from the liquid state to the gas state. And again, at that transition, that is going to be our delta H of vaporization. And that was the number they use in your book. It's 40.6 kilojoules per mole. Again, some books use a slightly different number, so you'll see some variance on that. And again, this does occur at 100 degrees Celsius. So we do want to get this into sort of the proper units so that we can get it to work with our kilojoules and our moles. So basically, we need to get this number into moles so that these guys will cancel out. So the first part of the calculation here will be pretty similar. We're going to take our kilograms, we're going to convert it into grams, and we're going to use the molar mass from the periodic table. To take our grams into moles. And at that point, we can use it with the molar heat of vaporization so that the moles cancel. So what we see here again, kilograms will cancel, grams will cancel, moles will cancel, and that will leave us the energy required to basically do that, to basically take 10.5 grams of liquid water at 100 degrees Celsius and actually convert it into 10.5 kilograms of water in the gas phase at 100 degrees Celsius. Again, a reminder, basically what we're talking about is we're starting right here at the liquid phase. We're going to the gas phase, and all of this is exactly at 100 degrees Celsius. There's absolutely no change happening here. We're just simply taking that 10.5 kilograms into gas at 10.5 kilograms. Again, at 100 degrees Celsius, no change in temperature occurring here. And again, that's why we use the heat of vaporization here, not something like specific heat capacity. Three significant figures really based off of our original number there, which was our 10.5, which had three significant figures. Any questions on that calculation? Okay. Just before we go off of this one, well, you can, if you wanted to, you could have used that other number that I showed you as well, which is like that 2260 joules per gram. So you could have converted your 10.5 kilograms into grams and then multiplied it by 2260 joules per gram. And you should pretty much get the same answer there, hopefully. And that would give it to you as what we got there. I'll get you 2373000. These would be joules, and then if we went, a few places this way, this would get us to kilojoules if you divide it by 1,000. So again, you can use it in joules if you needed, joules per gram. That conversion again gives you the same answer because it's basically the same conversion. All right, as we talked about earlier, again, anywhere in that sort of curve as you are transitioning upward, which basically means we're staying in the same phase, but we're changing the temperature. That is our specific heat capacity, as we talked about. Again, you want to make sure that you look things up in their proper state so everything works right. And again, that is the one that we saw earlier that we talked about that you do need to memorize that one. They want you to know that. But again, a note here, as you can see, if we are not in the liquid state, but we are, say, with ice or the solid state, the specific heat capacity is different for water. Same thing with in the gas state or steam, it also is different for water. So again, you want to make sure you get those things in the right state. So that you have the right answers there, obviously, when you do that. So it's a very common mistake. People will just continuously use that 4.184 number everywhere that involves water. But again, that would not be the correct number if we're specifically not in the liquid state. And this will be kind of covered, so we'll kind of go through that. And just a reminder of a calculation like we saw earlier here in chapter 10. Here we want to calculate the heat or energy. We have the mass. Obviously, we are changing the temperature here, and we are in the same phase, liquid water all the way through. So it is important, as we talked about before, to always do the final minus the initial, because when we talked about specific heat capacity, that really is the thing that's going to determine whether or not it's going to be exothermic or endothermic, right? And it's really that difference in the temperature. If your final temperature is less than your initial temperature, then you're going to have that negative or exothermic reaction. If your final temperature is greater, I think, than your initial temperature, then you'll have that endothermic type process. And again, it's important to do it final minus initial, because that does give you the negative sign if you need it, or the positive sign, obviously, if you need it. So in this case, when we do that, we do see here, we get something like 471 joules for our energy. Our energy here would be positive. Again, the temperature is going from 21 to 39, as it showed on that last slide, which means in order to raise the temperature, it needs to absorb some energy, which means it should be endothermic and should be a positive number, which is obviously what we see for the energy here. So we want to make sure, again, final minus initial, and we do end up with the correct answer. Any questions on that one there? Okay, so let's take a look at one where we're really sort of taking a substance from one phase to another phase. So let's see how we would do that. So here, we want to calculate the total amount of energy that's required to heat 20.0 grams of ice from minus 12 to steam at 115.0 degrees Celsius. So we're going to do a lot of sort of phase changes, and sometimes it's really good to draw kind of what's going on. We'll get back to these guys here in just a second, but let's just take a look at this here. So what you could draw is sort of our little heating and cooling curve that we saw previously. So we're going to kind of go this move, and a very badly drawn one, but we'll try our best here. We'll go this way, and we'll go this way. All right. So these kind of flattish lines that I very badly drew, that's 0 degrees Celsius. This is 100 degrees Celsius. And that's a normal sort of melting point and boiling point for something like water. So in this particular problem, we're taking 20 grams of basically ice, which is basically water in the solid state. And we want to take it all the way to steam at 115 degrees Celsius. And we're starting at minus 12 in this particular case. So when we think about where we're starting, we want to maybe think about the very first step. So the very first step would be we're somewhere about here, right? At minus 12 degrees, right? So the first thing that's going to happen is we need to take that ice at minus 12 degrees Celsius to basically ice at 0 degrees Celsius. So this would be like our very first step that we would need to do right here, is to take it from minus 12 degrees Celsius to 0 degrees Celsius. So let's talk about what happens when we're doing that. So our very first step would be to take it from minus 12 degrees Celsius to 0 degrees Celsius. And this remains ice, or the solid state, which means we are not changing the phase, but we are changing the temperature. So again, whenever you change the temperature, but not the phase, we want to use our specific heat capacity equation. So we would want to use our specific heat capacity equation here. So we're going to do our Q is equal to 20 grams, which is our M. Now, we are at ice, which is the solid version of water. So when we look up on that table for ice, the specific heat capacity is actually 2.03 joules per gram per degree Celsius. So again, here we would not want to use our 4.184 number because we're not at liquid water yet. So we're at ice, which is solid. So it has a different value of S. So that's an important little part there. That is S for water in the solid state. So again, you want to make sure that you don't just use that 4.184 number here. Now, our final temperature here is going to be 0 degrees Celsius minus our initial temperature, which is going to be minus 12 degrees Celsius. And when that's all said and done here, we are going to end up with 20 times 2.03 times basically 12 on that. Gives us something like 487.2 joules. It is positive because it's endothermic, right? We're taking something from ice at a lower temperature to ice at a higher temperature, so it's gaining temperature, so it would be endothermic. Any questions on that so far? So if we go back to our little curve here, we're now going to be sitting right about here. And by the way, just so everybody realizes, our goal is to end up way up here at 115 degrees Celsius. So the next thing that we need to do is actually take it from ice at 0 degrees Celsius to liquid water at 0 degrees Celsius. So that is the next step, is actually the phase change. So we're going to take it from solid to liquid at this point. And that is step number 2, which is to take it from ice at 0 degrees Celsius to liquid water, which is obviously liquid, at 0 degrees Celsius. So this is the part where we are changing the phase, but not changing the temperature. So that part of the curve is our delta H of fusion we need to do that. And again, here we would want to use it for our substance, and happens to be water. So that delta H of fusion is our 6.02 kilojoules per mole. R is that 334 joules per gram type number. Again, they're both the same. I'm personally going to use the joules per gram because, this number's in joules already. So I'm just going to go with that number. So everybody's kind of in the right units to begin with. So what I'm going to do is, again, here we have not lost any of the mass. So it's still 20 grams of water. I'm going to multiply it by 334 joules per gram, which is our delta H of fusion. Again, specifically for water. And when I do that, that will give me something like 6680 joules. Again, also going to be positive here. We need to put energy in to go from solid to liquid. It's an endothermic process, and we will end up with 6680. Any questions on that so far? Okay, so if we go back to our little kind of drawing here, we could see where we're at this point. We are now sitting at liquid water at 0 degrees Celsius. So the next process that would occur is we would take that liquid water at 0 degrees Celsius, and we would take it all the way up to liquid water at 100 degrees Celsius. So we need to take it from liquid water at 0 degrees Celsius to liquid water at 100 degrees Celsius. And here we are in the same phase. So all the way across this darker blue line, that is all liquid. So it all remains the same phase, but we change the temperature here. So our next step would be to take it, as I mentioned, from liquid water at 0 degrees Celsius to liquid water at 100 degrees Celsius. So again, here we are same phase, different temperatures. We go back to our specific heat equation at that point. And we would go, our Q is equal to, again, the same mass. We haven't dropped anything, hopefully. But now when we get to the S here, we are in the liquid phase here, right? So we're in the liquid phase here. And that is going to be our 4.184 joules per gram per degree Celsius number for S. Again, because we're in that window of liquid water, and that would be the specific heat capacity for it. So here we would use that 4.184 joules per gram per degree Celsius. Our final temperature is 100 degrees Celsius. Initial temperature is 0, and that will get us something like 20 times 4.184 times 100 gives us something like, I think, 8368 joules at this point. Any questions up to that point there? Okay. So just so we're clear, the number that we just calculated here, again, is positive, which is endothermic. That 8368, again, is the amount of energy to take your guy that started here at 0 all the way up to 100 degrees Celsius. And we can see we're getting close to where we want to get to, but we still have a couple more steps. And the next thing that's going to happen is we're obviously at 100 degrees Celsius, which for water is its boiling point, its normal change. So we're going to take it from 100 degrees Celsius liquid water all the way across to 100 degrees Celsius gas. So we're doing a phase change here for the fourth step. And that is, again, going from liquid to gas. So that's going to be our delta H of vaporization that we need to use here. And that would be our fourth step, taking it from liquid at 100 degrees Celsius to gas at 100 degrees Celsius. Again, that's going to be our delta H of vaporization. And for water, that is our 40.6 kilojoules per mole, or our 2260 joules per gram. So again, I'm going to use the joules because all my other numbers are in joules, so everything's going to be okay. So again, we would simply just take our 20 grams, multiply it by our 2260 joules per gram, going to get us 20 times 2260, 45,200 joules. And that is the energy that's required to go from the liquid state to the gas state. Now, if we compare that to the energy that's required to go from the solid state to the liquid state, which is right here, again, we could see that it takes a tremendous amount more energy to do that transition. About 6,700 from going from solid to liquid, to about 45,000 going from liquid to gas. So a lot more energy required to do that transition of liquid to gas. Any questions on that so far? Okay. Now, if we look at our little kind of map here, we may think we're pretty close, but we're actually not there yet. We still have one more step to go. We're sitting pretty much right here, but we need to end right here. So the last step would be this step here, which is taking our water that's now in the gas phase at 100 degrees Celsius to water in the gas phase at 115 degrees Celsius. And that, again, is going to mean we are going to use our specific heat equation here. So again, as you can see on all these ones that we sort of change temperature, we use our specific heat equation. And where am I going to put that? Let's see. Let's go with, let's go back here. So we'll do that. We'll do it here. Step number 5, I think it was, if I'm not mistaken, is going to take our Q equals ms delta T, and we're basically taking, again, gas at 100 degrees Celsius to gas at 115 degrees Celsius. And our Q would be 20 Also important here is we are no longer in the liquid phase. We are in the gas phase. So when we look up the specific heat capacity for gas, our water in the gas phase, it is 2 joules per gram per degree Celsius. So again here, not that 4.184 number. Our final temperature, 115 minus our initial, which is 100. And that's going to give us 115 minus 100 times 2 times 4, no, times 20. Going to give us 600 joules of energy. And again, that's the energy required to do the very last step there, which as we saw was right here, this step. So to fill in sort of our numbers, I think I just had 600 joules for that fifth step. The fourth step was 45,200. Our third step there was 8368. Our second step there was 6680. And our first step there was 487.2. And all these numbers are positive numbers. They're all endothermic. So the question is, how much heat does it take to go all the way across there from our minus 12 to our 115? And the amount of energy required to do that is simply adding all those together. So what we want to do is add up all those values that we just got together. So basically the total energy is basically step 1 plus step 2 plus step 3 plus step 4 and step 5. And this is really why I put everybody into the same units, because I knew I was going to add them all together at the end. Again, if you did some in kilojoules, you did some in joules, you want to make sure everybody really is in the same units. So we had 487.2 joules plus 6680 joules plus 8368 joules plus 45,200 and 600 joules. And if we put all that together here, we get something like 61335.2 joules, or if we give it in kilojoules, something probably like 61.3 kilojoules of energy is required to do that entire transition, take it from ice all the way up to 115 degrees Celsius. Any questions on any of those steps or what we did? Again, it's really a good idea to sort of draw the little diagram like I did, because a lot of times people will miss certain transitions and stuff like that. And it's a good way that you can kind of visually see what's going on. Any questions on any of those steps there? So let me ask you, what would happen if we had the same question, but the question was slightly different, and it wanted to know how much energy is required to take 20 grams of steam at 115 degrees Celsius to ice at minus 12 degrees Celsius. So this is basically the exact same question, but it's going in the opposite direction. So it's starting here and going downward. And really, the only thing that would be different is nothing really would be different in terms of the numbers that you got for each step. The only difference is the sign for each step. Instead of 600 joules for step number 5, going the opposite way, it would be minus 600 joules. And that's because the temperature would be opposite. The temperature would be 100 would be your final, and 115 would be your initial, giving you a minus 15 here and a negative number here. Coming the other transition, going number 4, going from gas back to liquid, the difference is the heat of vaporization would be a negative number. So you would actually get negative 45, 200. Going step number 3 backwards, going from 100 degrees Celsius to 0 degrees Celsius, again, your change in temperature would be 0 minus 100, which would give you a negative 8368. Delta H infusion going the opposite way, liquid back to solid at 0 degrees Celsius would be negative 334, which would give you a negative number. And lastly, going the opposite way, ending at minus 12 minus 0 would give you a negative number. So the only thing would be different if we went opposite is all these guys here would end up being negative values. And that means that you would end up with the same answer, except it would be negative, and the other answer would be negative. And the reason for that, again, is to imply that the way that we did the calculation going from solid to gas, that is all endothermic, all positive values all the way through in terms of energy. Going the opposite way from gas back to solid would be exothermic. Energy has to be given off, and that should be negative numbers all the way through. So again, you could do the same calculations. The only difference is, depending on which way you go, you will get either a negative number or a positive number. Any questions on any part of that calculation, how to do it? Those things. Okay. And again, I do highly recommend to kind of draw it as you're doing it. Again, it's very helpful to sort of see what's happening, sort of see the transitions and stuff like that. So let's talk a little bit more about intermolecular forces and sort of the different types of intermolecular forces that really do sort of help us understand the different boiling points or melting points that we may see for substances. Again, as we've seen many times here, that intermolecular force is that force between two molecules or multiple molecules, basically. And there's really 3 types of intermolecular forces. There's dipole-dipole forces. There's ones that are known as hydrogen bonding, and there's one known as London dispersion forces, or a lot of people just call it dispersion forces. No matter what type of intermolecular force we're going to see here, to be truthfully honest with you, they are all basically the same type of interaction. They're all basically that electrostatic interaction. And what that basically means is it's the positive guy and the negative guy. So ultimately, this is the attractive force that happens when we deal with intermolecular forces. There's sort of a positive side that's attracted to a negative side that gives them a way to interact with each other. And no matter which one of these 3 things here, that is ultimately what the type of attraction is. And again, just to reiterate, as we talked about before, our intramolecular forces are always stronger than our intermolecular forces. So this is a comparison of something like water. So water basically has 2 hydrogen-oxygen bonds. In order to break one of those hydrogen-oxygen bonds, it takes 934 kilojoules per mole, while the energy required to break apart one water molecule from another is our 40.7 kilojoules per mole. And that is obviously much, much weaker. So because it's weaker, this bond breaks first rather than this bond or that bond, which takes, as you can see, a lot more energy to sort of break those guys apart. So intramolecular forces, which is essentially your covalent bonding, also your ionic bonding, always going to be stronger. So looking at our first type of intermolecular force, that is what is sometimes referred to as a dipole-dipole force. And if you remember dipoles, we sort of came across it when we were dealing with polar molecules. And if you remember, for example, if you had something like HF, fluorine is more electronegative, you could draw that little arrow. That is what is known as a dipole. Something like water, which is a polar molecule, has a dipole moment, which is an overall side that's more negative, overall side that's more positive. So remember those dipole moments, that little arrow makes kind of like a plus sign, is the side that's more positive. always points to the side that's more negative in a particular molecule. So really when we see sort of dipole-dipole interactions, they're really for polar molecules interacting with polar molecules. The basic idea of that is just this basic drawing here. If you have a polar molecule, you have a fixed side of that molecule that's more positive, a fixed side that's more negative, and when it gets near another polar molecule, that guy also has a fixed side that is positive and a fixed side that is negative. And it is that opposite sides in terms of charge that are attracted to each other. So the negative side of one polar molecule will be attracted to the positive side of another. And that is our dipole-dipole interaction. That molecule or that force, that basically holds together that one entire molecule with another one. So dipole-dipole is a relatively strong interaction. And again, it is typically the intermolecular force of choice for polar molecules, as we will see, that really cannot hydrogen bond. And we'll talk about hydrogen bond is here in just a second, but they're basically guys that don't have the ability to hydrogen bond, but can interact this way. And that's what we see here when we get a whole bunch of these polar molecules together. They really do try to maximize the attractive forces. So the places where positive sides and negative sides of molecules are near each other, and try to minimize, positive guys near positive guys, negative guys near negative guys. But no matter what happens, there's always going to be some areas where positive guys are near positive guys, negative guys are near negative guys, but they really try to keep moving until they maximize the attractive force between the opposite charges and minimize the repulsive force between two opposite charges, a positive and negative. And again, remember that if something is a polar molecule, it has a fixed dipole moment. And again, what is important about that is no matter what the situation is, there's always going to be a positive side and a negative side. So those guys always have that happening. They always have that positive, negative side. They're ready to go in terms of interaction. Because of that, they don't have to wait to become positive or negative. They have sort of that fixed side that no matter what the situation is, always going to be positive and always going to be negative. Another type of between atoms with different that's good. Another type of intermolecular force is hydrogen bonding. And really, hydrogen bonding is a type of dipole-dipole interaction. And hydrogen bonding is a very strong intermolecular force. It is actually the strongest intermolecular force that we come across. And it is important to sort of understand what that is. And it involves a hydrogen that's bonded to a highly electronegative atom like nitrogen, oxygen, or fluorine. So if you look at the periodic table, that is your run upper right of the periodic table. Remember, fluorine is the most electronegative you could have. So this type of interaction is what we see in water. So if we look in water here, water is a polar molecule. Again, the oxygen being more negative, the hydrogen being more positive. And when we get two of these guys together, we have a hydrogen that's bound to an oxygen in one water, hydrogen that's bound to an oxygen in another. And again, it's that negative side of one water attracted to the positive side of another here. And that is what is known as hydrogen bonding right here. So you may say to yourself, well, obviously, if you have hydrogen, they could do that. So if we look at something like this, like CH4, it definitely has hydrogens. It's got 4 of them. But if you remember, the carbon-hydrogen bond is actually nonpolar, which basically means that there is no separation of charge here. There's not a positive side. There's not a negative side. It's kind of neutral, if you will. And it has no way to hydrogen bond, even though it's got a ton of hydrogens. It has no way to do that. So in order for something to have the ability to hydrogen bond, it does need to be a hydrogen that's directly connected to a nitrogen, oxygen, or fluorine. So for example, if you took something like NH3, NH3 can hydrogen bond. NH3 is polar. This is trigonal pyramid. This is a polar molecule. Hydrogen being more positive, nitrogen being more negative here. It is actually able to hydrogen bond. We have a hydrogen that is directly attached to a nitrogen. It's going to allow it to do that. So sometimes people think all you need is a hydrogen, and that is not the case. Again, this guy would not be able to hydrogen bond because it doesn't have the right type of hydrogen. So it's very important, that distinction. You got to have that hydrogen that's really directly bound to nitrogen, oxygen, or fluorine. I would say nitrogen and oxygen are probably the most common ones you'll see that occurs with that. So what is hydrogen bonding sort of choice? Well, hydrogen bonding's choice is, this is really for polar molecules that can hydrogen bond. And that's sort of the difference between hydrogen bonding and dipole-dipole. Hydrogen bonding and dipole-dipole are really the same thing. They're both really dipole-dipole interactions. But when you have something that is a dipole interaction, it cannot hydrogen bond. So for example, if we had NF3, right? This is a polar molecule. It cannot hydrogen bond because A, it doesn't have any hydrogen bond, so it cannot hydrogen bond with itself. So this guy would most likely use dipole-dipole interaction. While again, something like water, which obviously does have hydrogen attached to an oxygen, can hydrogen bond, it would use hydrogen bonding. So in terms of strength, hydrogen bonding is the first strongest. Dipole-dipole is next. And let's take a look at some of that. So here again is some hydrogen bonding happening between water molecules. By the way, when we talk about these intermolecular forces, a lot of times we talk about it in terms of it bonding with itself, like the same molecule sort of bonding with itself. But there can be other like crossovers. So for example, if you had something like this is methanol, and you had something like water, these are two different guys. But water is polar, which again, the hydrogen more positive, oxygen more negative. This OH group here acts the same way. This is negative, this is positive. So there can be hydrogen bonding happening between these two different sort of molecules as well. So it doesn't always have to be the same molecule with itself, but it can be other ones as well.
Some polar molecules have unusually strong intermolecular attractions called hydrogen bonding. These attractions occur in molecules where hydrogen is bonded to fluorine, oxygen, or nitrogen. The interaction occurs between the hydrogen of one molecule and an unshared electron pair on the more electronegative element in another molecule. The orientation of hydrogen fluoride and water molecules in the liquid states of these substances is determined by
That was exciting. All right. So, so the effects of hydrogen bonding, as we could kind of see here, we do see something that has the ability to hydrogen bond, has a very high boiling point. These guys with sort of a not really an ability to hydrogen bond, you have a lot lower of a boiling point, as you can see here. Again, even though there's hydrogens here, we don't have a hydrogen that's connected to an oxygen, nitrogen, or fluorine, so it cannot hydrogen bond like water. That leaves us sort of our last type of intermolecular force, which is sometimes referred to as dispersion forces. And dispersion forces are really for our nonpolar molecules. So it's really how nonpolar and nonpolar molecules basically interact with one another. And again, if you remember, nonpolar basically means we're sharing electrons sort of equally. There's really no positive side or negative side that's sort of happening. So what happens when we deal with sort of dispersion forces is there's sort of a temporary attraction that occurs. So a temporary attraction that occurs between different molecules. So for example, if we had say these two nonpolar molecules here, and electrons are moving around. So if for some reason all the electrons decided to kind of go to the left-hand side of the molecule, what would happen is that molecule A, which normally does not have a charge or a separation of charge, will temporarily gain a negative charge on the left-hand side and a positive charge on the right-hand side because all the electrons decided to go to the left-hand side. And if it's sitting next to molecule B, which normally doesn't have a charge either, once we have all this positive charge on the A, the electrons in this guy are going to decide, hey, I'm attracted. And all the electrons in B will head to the left-hand side. And now, before you know it, you had two molecules that started out with no charge separation. And now they have gained this temporary charge separation that occurs between them. In addition, by gaining this temporary charge on each of these guys, they now have a way that they can interact with one another. So they can temporarily sort of come together and create a charge or an attractive force between these two molecules. These are temporary charges because what's going to happen is eventually these electrons will decide, hey, let's go back the other way. We'll just head back the other way. And this bond here will break apart and new bonds will be formed. Other ones will break apart and new bonds will be formed. So these are very temporary sort of attractive forces that occur. They are referred to sometimes as instantaneous dipoles because they don't normally have one, but they just quickly sort of develop one because of how the electrons moved around. They also can be caused by something temporarily. So you could temporarily, for example, if you had a nonpolar molecule and a polar molecule comes by, it will temporarily cause this nonpolar guy to have its electrons sort of go this way, right? And we get this temporary charge that occurs here between these two guys. Again, as soon as this guy kind of moves away, it will kind of back off and stuff like that. And dispersion forces, which are very weak forces, they're the weakest of our intermolecular forces. Now, when you compare sort of dispersion forces to dispersion forces, so two guys that basically will use dispersion forces, molecular mass is important. So the more molar mass, the more electrons, there's a greater chance that these electrons will start to move and create these temporary charges. So in terms of something like methane that we saw earlier, which is that CH4, this guy here would actually use dispersion forces as its way of interacting. Again, it's that temporary way to interact is how nonpolar guys interact with each other. And that's what this picture sort of shows here, this temporary attraction between these guys. So in terms of strength, as I mentioned, the strongest out of all of those is hydrogen bonding. The next strongest is our dipole. And the weakest out of all of them is our dispersion forces. And you may be asking, well, dispersion forces and dipole, they kind of seem like the same thing. And they are the same thing in terms of sort of their interaction, but they're different because when you have hydrogen bonding or dipole, and you have a polar molecule, there is always a fixed side that's positive or negative, like I was saying before. No matter what the situation, you always have that. But when you have a nonpolar molecule, it is essentially neutral. Something has to happen to it to create that temporary positive and negative charge. So that's the real difference between those things, especially when we get to dispersion forces. They are temporary because something needs to happen to those guys to allow them a way to interact with each other. We talked a little bit about solubility, and we'll talk about it probably a little bit more in the next chapter, but something known as like dissolves like is a very common phrase. And that means that typically polar things are soluble in each other. Nonpolar and nonpolar guys are also soluble in each other. They mix really well. And when you go polar and nonpolar, they're typically insoluble in each other. They do not mix really well. So these guys are soluble up here. And that's because when you put a polar guy and a polar guy together, they're probably going to use dipole and dipole, or hydrogen bonding and hydrogen bonding. You put a nonpolar and nonpolar guy together, they're going to both be using dispersion forces. But if you try to mix a polar and nonpolar guy together, you have somebody that's trying to do dipole dipole and somebody trying to do dispersions. They have no long way to interact with each other. So a very simple example is like you take oil and water, right? Or oil and vinegar type salad dressing, right? You can mix it, right? It will stay mixed for a while, but eventually what will happen is everybody will separate out because they have no long way to interact with each other and keep those sort of interactions happening. Any questions on that there? So again, dispersion forces does become stronger as the size of the atoms increase, and dispersion forces, because there's a lot more electrons, a greater chance of those electrons kind of moving around. So in general, as I mentioned, the stronger the intermolecular force, the higher melting and boiling points we would expect to have. So if you can identify something as using hydrogen bonding, we definitely would expect it to have a higher melting point and boiling point than something that is using dispersion forces. So let's take a look at some of those. So between these two things, which one is capable of forming a stronger intermolecular force? So if you're not really sure what's happening here, you might want to kind of sketch it really quick. So if we sketch this guy really quick, this is a nonpolar molecule. And nonpolar molecule is going to use pretty much dispersion forces as its intermolecular force. Water, as we saw before, is a polar molecule, right? Also has a bond between hydrogen and oxygen, which means it can hydrogen bond. And again, between these two things, the water and the hydrogen bonding is a much stronger intermolecular force. So we would expect it to have the stronger intermolecular force. We also would expect it to have the higher boiling point and melting point. Any questions on that one? Now, if we look at two structures here, for example, they are basically the same in terms of their formula, but the way they're arranged is different. If we just dissect this and look at this, we see this part of this molecule, which is essentially nonpolar. But we do have this part, which is a polar part of the molecule. Again, the oxygen being more negative, hydrogen being more positive. We have a hydrogen that is directly attached to an oxygen. This guy here can hydrogen bond because of that. Again, not the entire molecule, but this little part in the square with the OH group can do hydrogen bonding. When we come over here, again, all this is pretty much nonpolar. A little bit of polarity here, but important here is I do not see a hydrogen attached. So this guy can do no hydrogen bonding. So in comparisons of these two, because the guy on the left has the ability to hydrogen bond, which is the strongest intermolecular force, we would expect this guy here on the left to have the higher boiling point of the two. Any questions on that there? That's almost a safe bet. If you got something with hydrogen bonding, pick it as your highest boiling point out of them all 99% of the time. Any questions on that too? All right, so which of the ones is the strongest intermolecular force in a noble gas? So noble gases are nonmetals. They also are chemically inert. They don't interact really well with other things, but with themselves. So they definitely would not use hydrogen bonding as they're not going to be polar. It would be A, which is basically our dispersion forces. And again, nonmetals and nonmetals coming together, that is typically what those guys would use. Here again, we need something that's going to be polar, which is not going to happen with noble gases, does not have hydrogen, and they are not ions. So those guys would not work. So it is going to be dispersion forces here. Any questions on that one? Which of the following would have the highest boiling point? So again, if we want to go through this, we want to maybe think about what is happening here. So water, as we've seen in a number of examples, has the ability to hydrogen bond. So that should have a pretty high boiling point. HF, that's a hydrogen attached to a fluorine in a polar molecule. So it also could do some hydrogen bonding. So it would be pretty high. NH3 is our polar guy, which we talked about before. Hydrogen attached to a nitrogen. It also could do some hydrogen bonding. So it's going to be relatively high. N2 is a nonpolar molecule. Again, nonpolar molecules are going to use dispersion forces, which are weak. They're going to have a pretty low boiling point here. And over here, this is ionic, right? This is a metal and a non-metal. So take a second, think which one you think should be the highest boiling point out of these. And you may say to yourself, well, it's hard to choose since these all are hydrogen bonding. That should have our highest. And it would be true, except that we do have an ionic bond here. And an ionic bond is a intramolecular force, right? And all of these other ones, A through D, these are all intermolecular forces. So E is actually the right answer here. And that is because, as we talked about at the beginning here, any intramolecular force will always be greater in terms of its strength than any intramolecular force. So intramolecular forces are always going to be greater. Just make sure I said that right. Intramolecular force is always going to be greater than any intermolecular forces. So our ionic bond here should be the strongest. Any questions on that there? Okay. So we'll stop for now here. And like I said, we're going to do the precipitation reaction there in lab. And we may just finish up the few remaining examples here in this chapter, and then we'll do the lab. All right, I'll see everybody in 15 minutes. Make sure you put